Hi, my name is Ava, and in this video we're going to explore different approaches in computer vision through the lens of agriculture pest classification. For many years, AI followed the rule, more data means better models. But within the past 5 years, more and more researchers are supporting the idea of less is more, especially when the dataset is noisy. Might be an intuitive idea, but they demonstrate this mathematically challenging the traditional bigger is better intuition, highlighting the importance of data curation. And that gives an interesting angle to view challenges like datasets such as AgroPest 12, containing around 13,000 web-crawled images with significant variability and noise. Our goal is to explore and develop different methods for this. We develop our work across 3 branches: machine learning, deep learning, and transformer, starting with baselines and progressively adding enhancements, such as I'll pass on to Jeremy now for the machine learning branch.
Hello, I'm Jeremy, and this is the method I'm going to demonstrate. A classical ML approach using HOG plus SVM and a little bit more. My SVM methods follow a typical classical ML pipeline, preparing the data, extracting handcraft features, optionally adding segmentation, and finally training an SVM classifier. First, I clean the dataset by removing and fixing mislabeled samples and filtering out extremely small and weighted bounding boxes. I also manually inspected the dataset to ensure data is clean and accurate. Because the dataset is quite imbalanced, I applied data augmentation to bring the minority classes in scale to the dominant classes and gave the SVM a more balanced training distribution. I experimented with preprocessing using mobile SAM to generate cleaner object masses for the training crops. Then I expanded the feature set beyond HOG. Each of these handcraft addition contributes more improvement to the score. The RB I read off a paper on tomato pest classification using Surf, which is a non-free library, so I look up the web and substitute with a standard library, which is somewhat similar. The initial model prediction started off with a mere F1 score of 0.23 with only HOG plus SVM, and slowly improved the score with new features and different settings. My final models combine mobile SAM crops with full feature set and push the weighted F1 score up to about 0.46. The main limitations remain on the field pest classes, where recall is very low, as you can see in the reports, meaning the SVM often missed it. Let me show you the code.
Okay, all right. So the training's done. I'll do some editing so that to edit out all the extra parts. Yes. So the whole video after this one is 52 minutes. The average score is still 0.47, and you can actually see that some of the classes is actually doing a little bit better, but some of them is just awful. Like the beetles, the earring, and the slug, and the grasshopper. These are the worst. They've got a lot of missing. Look at you here. It's just horrible. So thank you for watching.
Thank you, Ava. Thank you, Jeremy. This is James Yang. Now I will present my experiment on deep learning method. Basically, it serves as a benchmark for later comparison to understand the efficiency and accuracy among different methods. We picked YOLO V8N as the baseline method, as the whole dataset was designed in this way, together with a faster RCNN in ResNet50 backbone, which is mentioned frequently in the articles that we have reviewed. Now I will run the test on each of them, and due to time constraints, I will fast forward the whole process. During the training, I realized ResNet50 was really computationally complex and took a long while to finish. I then tried mobile net backbone, which is more lightweighted, approximately 3 times quicker than the previous one. Here's the data collected from testing each of the models. We can see YOLO V8 almost equalized to faster RCNN's method, even though it took a significant less running time. To further analyze their performance, I also twisted the text image a little bit by adding Gaussian blur function and Gaussian noise function to produce even blurrier and noisier images and run my models on those. Under these circumstances, we can see faster RCNN is actually more stable in extreme situations, while the performance of YOLO is downgraded to a large scale. Among the 12 insect classes, we also notice that some classes outperform the other in terms of classification accuracy, like weevils and bees, whereas caterpillars and earthworms are hardly identifiable. The reason might be because weevils and bees have more constant appearance, where caterpillars have completely different life cycle, and earthworms are also vary in body shape and color.
To delve deeper into the why, based on James and Jeremy's data, the reason these models struggle particularly in certain classes, we speculated that there is the variation throughout their life cycle or within the class, and they have similar shape, color, or background. They're often found in clumps or hidden in grasses or picked up by other objects easily, and these quote-unquote bad images were included in training more often. So first we used Jeremy's code to filter some obvious bad images out. This is the criteria we used. The second prediction was the noise of the real-world dataset altered things like color and texture so much, perhaps, that it is the shape that is the most reliable cue. And the YOLO box wasn't always correct. It was only for about 80% that it was correct, so maybe skipping the labels altogether might give slightly more accurate results. And so we tried applying the segmentation model with masks, and the result shows that it didn't improve performance, though we did gain 25% improved training speed, likely because many samples were too noisy or occluded or misannotated for shape cues to be recovered. Changing parameters like area or edge density just didn't really yield successful accuracy gain, but it was still worth noting how well it did with a single sample. So that led our next focus onto background separation. Can we feed more negative samples to the CNN detector? That might help with the accuracy. So to test this, we fine-tuned our baseline YOLO model on 4 different negative sample datasets for different types of soil, crop, weed, and leaves, and the results were mixed. Ones that were already high contrast and visually distinct gained precision boost in general, but ones that were already poorly localized, the model just didn't see them. So overall, slightly better precision, but also slightly higher recall losses, but depends on the class, and that gives a slight advantage in avoiding false positives. Whether this is useful depends on the applications. If, say, resource cost is higher for every trigger from detection than the cost from missing real pests, like sending your drone to spray pesticides, then this can be useful, but if we're trying to catch every little warning sign to preserve crop health, we wouldn't want to do this. Of course, there are many different ways we can configure and interpret this, so this is just one example. Now comes the transformer part. These self-supervised models with vision transform embeddings like Dino can find objects without bounding boxes. Its global self-attention property can capture the subtle features like the fuzzy hair of a caterpillar or the smooth wet skin of a worm and enable overcoming clutter or poor lighting, etc. So we predicted that combining any classifier with a vision transformer will improve accuracy. We used a linear classifier, and that achieved around 94% accuracy and up to 96% on the difference split ratio. That's 15 times better than the CNN average we saw earlier with around 80% accuracy. It required 98% less training time compared to YOLO. That's twice as fast as SVM, though it's important to note that YOLO involved detection, which is a much heavier task compared to just classification. But it's 17 times faster, the YOLO is, at inference speed than Dino version 2, so it still makes a strong choice for real-time use. But for offline batch processing, the transformer clearly dominates in speed and accuracy. So we can compare different classifier heads, like linear SVM, shallow MLP, and they pretty much yielded the same results. And what we can infer from this is that the vision transformer extracts the features so well that its encoding alone is responsible for almost all classification. So choosing a different classifier or fine-tuning it further probably won't even help much with the accuracy unless we opted to building a model that overfits our dataset. We then look at the remaining 6% of the error and wonder, can we find what the source of the error is and can we reduce them? Here we predict that the fundamental mislabels that exist in the test lead to the wrong ground truth, and it has to be related to the bounding boxes or annotations, assuming that the dataset curator used YOLO to find these data from the web. We've seen how YOLO struggles with noises, so can we measure how bad then these YOLO labels or the bounding boxes are? How about comparing the results of the two vision transformers output, one that only sees the cropped image and one that doesn't, the one that sees the whole image? That said, we can compare the distance between these two embeddings in the vector space and estimate how bad these boxes are. In other words, how far away from quote-unquote the ground truth defined by the vision transformer, which we assume is represented by the class centroids, that is the average points of all data points within a specific class, which divergence to almost all these forms give enough data. The cropped images is just a tiny bit better. When you look at the worst performing images, the ones with the furthest distance from the class centroids, that is, we could observe that the majority of the bounding boxes were generally good, though these are not necessarily indicating that the images weren't free from cluttering issues. In those cases, the model often missed detection, but they still often captured a pretty well fitted bounding box to the total area size of the single isolated class sample, ignoring the rest of the clutter, however. It's these ones that are problematic. So can we find them systematically? They definitely do exist, though right now it's a little vague to decide what is suitable for training or validation or testing. We haven't really defined a target operating condition even. So we could perhaps apply what we just learned about machine learning and CNN here and compute how likely there is a pest in the bounding box, how likely the edges from the masks match our expectations morphologically, and how likely the background outside the boxes match our expectations semantically. And in other words, calculate the quality score for each image based on earlier results, all combined. By doing so, we hope we can effectively find images that score low because of clutter, blurs, noises, etc., while keeping the ones that contextually make sense, but maybe err on the side that have unclear shape of or focus. So the idea is to filter the original dataset based on the quality scores. And we train our earlier architectures from the machine learning to CNN to transformer on the filtered datasets. We can see if they obtain better results than when they were trained on the original dataset. If that succeeds, we've effectively created a way to clean a large web crawl data suitable for training for any model with a few knobs and parameters that we can play around with. For this to work, we need some sort of reliable ground truth for the exact morphology of the pest. For this, we can define a small set of manually verified samples that clearly show the morphology or features for each class, or we can use cluster centroids of each class, which Dino version 2 embeddings almost always form even amidst noise, also known as unsupervised seed extraction. So for comparisons, we've taken the simplest versions of our 3 pipelines, and we've reduced the epoch to 20 and retrained and tested on both the original dataset and the Q-score filter dataset, taking out the bottom 20% with light mode, and the moderate mode would take out the 40%. That's a lot of data lost, so in the future work, we should probably soften the weights instead of removing them altogether, or use reinforcement learning to adjust the numbers that lead to the best performance. Now, the result was as expected. We gained some accuracy and faster time to completion. The baseline machine learning SVM gained about 2 to 3% gain in accuracy, MAP and AUC, as well as F1 and recall. The Dino linear model gained about 4 to 5% MAP and reached that's 99% MAP and AUC. Speed and inference time also halved with each filter, which is aligned with the volume loss. Let's jump into limitations. We are nowhere near considering every possible contributor to true loss. We can't really untangle every factor and say, this 7% loss is only from blur, because they often interact with each other. Likely, there's more unknown unknowns than we think. The semantic filtering still suffers from the chicken and egg problem. We cannot fully resolve incorrect or ambiguous labels, as the method still fundamentally depends on the correctness of the model, which depends on correct or suitable data, which is defined ambiguously. Models trained on our filtered dataset cannot be directly compared to other models trained on the original dataset, and the results cannot be generalized to mainstream comparisons. And it removes, crucially, these hard edge cases, the per class thresholds or reweighing can partly resolve this, but this means the model will not learn about rare species or things that are really important in the context of agricultural settings. So this could be mitigated by improving the selection criteria or by adding a human in the loop review step, but it defies the purpose of auto filtration pipeline. So that is why in future works the goal should not be to delete anything difficult, but to reduce harmful ambiguity or mislabels and explicitly study the impact of remaining hard factors, incorporating these context-aware embeddings that consider factors like illumination, motion, environmental conditions, and stuff. So in this regard, more data is necessary, but how we curate and handle it is more important than just the amount of data overall. We're going to end with this presentation with no amount of random stock images can replace multidimensional reasoning combined with domain knowledge. Take, for example, the Depth Anything 3 released just a few days ago can take any number of images to create a feed-forward geometry reconstruction by simply using vanilla Dino version 2 transformer, which we just saw earlier, and proves that it can beat the state-of-the-art models by 44% on pose estimation and 25% on multi-view geometry. We can take this into a Pest scale and it would yield interesting results. Hybrid models open the possibility of latent compression or on-device inference that enables real-time Pest monitoring on low-power hardware, which would help with collecting more diverse samples and reduce class imbalance. That extending this pipeline to a 4D representation or burst sequences may improve stability by leveraging motion cues or capturing insects at multiple angles or focus levels. And we could take this further and look into what specific environment each class or species prefer and fine-tune the model with it. That's just one example of combining the domain knowledge. Overall, we've seen how the computer vision has evolved in history to tackle the challenge like insects classification in real-world, noisy, messy agricultural setting. We've seen how machine learning alone was much less practical to be a useful application, and how deep learning could improve this with better detection and segmentation, but were limited in the sense that it lacked fundamental understanding required to be a truly versatile, deployable model in real-world settings. And by taking broader context into learning with things like transform embeddings or background domain knowledge, we've observed that we would be able to mitigate some of the real-world challenges. We acknowledged that this was one of the possibly infinitely many different angles to tackle the challenges with, and we acknowledged that why data curation is often a bigger bottleneck to the performance more than any heuristic in the modern computer vision paradigm. And for a model to produce a better result, sometimes less is more than over-engineering the solutions. But when it comes to the rare species and things like that, it's important to have many more data. So more data is true, more is true, but less is more is also true. Thank you for watching.